Okay, so for the following, we will have to find the formula for v of t using Laplace. So let's first work with the circuit for when t is less than 0. Okay, so that way we can find the initial condition of vt. So when t is less than 0, the switch is at this position, so we can just ignore all of this. So we have the following. So this is v of t, the capacitance, our resistance, and then VO. Okay, so pretty much we're assuming the circuit looks like this for a very long time. So obviously this becomes an open wire, but there is still a voltage of v of t at this region, and this v of t is pretty much being induced by this because there's nothing blocking the path here. That means when t is less than 0, v of t is equal to VO, and pretty much when t is equal to 0, the switch now moves to here. But obviously voltage at a capacitor can't change instantaneously. So that means at V0, it's equal to VO. So now let's work with the circuit when t is equal to 0. So now we have this current source, IO. Hold on, let me redraw this. There we go. Then we have our capacitance. So C, then R, and then all that. Now, the the Laplace of R is just going to be R. The Laplace of IO is just going to be IO of all over S. Now the Laplace of this is going to be where the tricky part comes in, because our initial condition is not 0, it's actually VO. So we know current, our I of t is equal to the capacitance times V of t all over dt, so dv of the change in voltage over the change in time. If we take the Laplace of this becomes Is. This is equal to C times S times V of S minus V at 0. And we know V at 0, that's VO that we got from here. So now these two, the port here, we will have to add like a current or voltage source. So we can do either one of two things. We can add a voltage source like this, where the voltage source, we will have to isolate for this to find what the voltage should be. So let's first FOIL in our C value. Okay, so we have to isolate for this. So we see our voltage source, it will have to be VO all over S. Okay, but if you don't want to go that route and you want to go with the current source instead, you can pretty much add like a current source moving in this direction, and it's pretty much going to be C times VO, okay, because that's what IS is equal to. So that would be your current source. Okay, so let's go with this one. Okay, so we'll get rid of this and include this into here. So our circuit will look something like this. So this is R. Then we have our capacitor with voltage Vs. Okay, it's not a Vt because we're Laplacing everything. Then we have a current source here of CVO. And then the capacitance here. The Laplace of the capacitance is 1 over SC. Alright, now we're trying to solve for, let's get an equation to represent Vs. We see Vs will be represented by this whole node here. So it'll be Vs. So let's have a current moving in this direction, a current moving in this direction. And we have these two moving in this direction. So it should be the following. Vs over R plus Vs over 1 over Sc, which will just be Vs times Sc. That's equal to I0 of S plus C times VO. Okay, so we just need to isolate for V of S. So we'll get that out. Okay, so looks good so far. Next thing we're going to do is, what should we do? Let's times everything by R. So we have Vs is equal to, times 1 plus Rc times S is equal to R over S times IO plus Rc times VO. Okay, and the time constant is equal to Rc, if you remember from first order circuits. So we can replace all the Rc's with time constant. Okay, and now let's divide by 1 plus time constant times S. Okay, now next step we have to do is, let's factor out time constant from both of these. So this one will be, let's do it on the next line. So it'll be S times T times 1 over time constant plus S. And this one, we take out the time constant, so 1 over time constant plus S. And we see these two should cancel each other out. Now I have my S alone, just like how I want it. Now I can finally do inverse Laplace to start solving for this. I'll bring this time constant up here. That way I have like all my S's out neat and nice. So the inverse Laplace of this, so we can take the VO out here, and we'll do 1 over S plus 1 over the time constant. And this we can represent it as the following: minus 1 over the time constant. And that will be VO e to the power of minus 1 over time constant times T. Okay, so that's the first one down. Now the second one is this one. We will probably have to use partial fractions to solve for this. So we have R IO all over time constant all over S times 1 over time constant plus S. That will be equal to A over S plus B over 1 over time constant plus S times everything by this value. So we'll have R over IO over the time constant is equal to A times 1 over time constant plus S plus B times S. Okay, so when S is equal to minus 1 over the time constant, B will be equal to minus IOR or RIO. And when S is equal to 0, A will be equal to RIO or IOR. So we can write A as IOR all over S plus minus IOR all over 1 over tau times time. So 1 over time constant plus S. Now let's get the inverse Laplace of both of these. Okay, inverse Laplace of 1 over S, that's just 1, so it's just IO times R times 1. And then this one, let's rewrite this as like this. So we can just write this as minus 1 over the time constant. So it will be e to the power of minus 1 over the time constant times t, because this whole thing is just a. And then we add this to it at the end, okay? So our final formula for v of t will be VO e to the power of minus 1 over the time constant times t minus IOR times e to the power of 1 over the time constant times t plus IOR when, or for when t is greater than or equal to 0.